What is this circuit board, you might not be wondering? Well, this is a prototype I am doing for a Midwest Gaming Classic workshop. Dan Lucen, who runs the show, asked me if I wanted to do a workshop this year since we didn't get to do the Z80 Note workshop last year. And I'm like, sure, but I don't know what I'm going to make. So I went online and I found what components were readily available. Like this AT Tiny 1616, which is very similar to what I'm using in the watch project, which I am still working on the video for that. Just stay tuned. Biggest difference here is this one has a lot more I/O, so we can have some buttons. So I was thinking making something like the Arju Boy. This is a little game system that you can get. I think it's like $60 or $70. I bought this at, what was it called? Portland Retro Gaming Expo a few years ago. Slowly but surely been working on a Boulder Dash clone called Garbage Miner 2049er. It's like in the future, humans have to mine their own garbage. So, I was kind of familiar with making, monochromatic games with this style screen. Although this uses a ATmega 32U4, which they're kind of hard to find at the moment. So my thought was, what if I found the cheapest, most readily available 8-bit microcontroller with a lot of I/O, which would be the 1616, and made something like the Arju Boy around it. So that's what this prototype is. Got like a piezo, a SPI OLED screen, and just a regulator. Obviously, it'll be smaller for the real one. And then buttons, which I've attached directly to the I/O using the internal pull-ups. So this would also be a project with minimal external components because I think the Z80 Note was a little overly complicated. All right, so let's talk about the schematic where I took this prototype and I made it into a schematic. Then I'll order the boards, which I've already done, and we'll assemble it, and then we'll talk about how to code it.
Okay, I'm using the new version of Snagit that I downloaded. It's still in trial mode, but if it works, and by works, I mean I edit a video using the sample footage and I'm happy with it, I will spend the $60 for the real version because this one captures my whole 1440p screen. The previous version of Snagit only did 1080, so I was always having to, when I was capturing stuff on my computer, I was having to do this, right? So yeah, okay, let's take a look. Here's the AT Tiny 1616 SNR, that just means tape and reel or whatever. Yeah, okay, over here, this is kind of superfluous, but I've added a 32768 hertz crystal. This thing has a real-time counter inside of it, which can act as a real-time clock. So we've got, well, I actually have two crystals here, so you can, whichever one you have, surface mount or a can. I got 22 puffs to ground. Yeah, so if you leave this thing on, it can go into sleep mode, and then you could use it as a clock. Here are all the buttons, just standard tag switches. These are my ground pads near the lanyard clips. Here's the SPI screen. I just created this part myself. Why are there two of them? Oh, you probably can figure it out already, but I'll keep you in suspense. Here's a piezo speaker connection. See how I use the same value resistor for both the piezo and the LED. Here's the programming port, UPDI, Universal Programmable Debug Interface. I'm using Atmel ICE, but you can actually rig up a Arduino to become a UPDI, and there's also Arduino libraries to drive this series of chips. So hopefully there's an Arduino fork done before the show. So here's the USB mini, got the cap on it. Then I was flying by the seat of my pants. I just went and I found the cheapest, most plentiful LiPo charger. It's very simple. It doesn't even have a battery indicator. It's pretty slow too. It's 500 milliamps, but it appears to work. So I slapped it into my thing. So we have the 5 volts, comes in, it charges the LiPo. Then there's a power switch, which you could always leave on if you want to use the real-time clock. That goes into the 3.3 volt regulator, and then that powers the CPU, microcontroller, and the OLED. There is a negative with 3.3 volts, and that is that it limits our speed. So this is why you should always RTFM. If you look at the chip here, speed grades. 0 to 20 megahertz, 4.5 volts. 0 to 10 megahertz, 2.7 to 5.5 volts. I have tested it. You can run it faster, but according to the specs, if you're running this device at 3.3 volts, that means you're going to have a speed downgrade. And that happens a lot with these. I mean, this is technically a 5-volt device. That doesn't mean you can't run it at lower voltages, but it does mean if you go lower than its spec voltage, you're going to have a speed. You're going to take a hit on speed. So this thing is going to be slower than the RG Boy. The RG Boy is 16 megahertz, although this thing is way cheaper because I love cheap. All right, so this is the front of it. So we have a vertical or horizontal orientation for the screen. Then we've got 3 buttons. The RG Boy only had 2 buttons, B and A. So I added menu. Really, really simple. Like you'll solder your LiPo on here manually. Then you've got the charge circuit, a USB for charging, power switch, 3.3 volt regulator goes into the screen and the the chip. Let's get the rear view on. Rear view mirror. Here's the programming interface. So I'll just use jumpers for it, but I'll probably make an adapter for the event. UPDI is pretty handy because if you have the ICE, you can program it and debug it with a single line versus the older ATtinies where you needed what? Clock data. Oh yeah, you needed MOSI, MISO, and clock and reset. So you can do this with 3, voltage reference, ground, and debug. It's pretty cool. So here's the 2 crystals. On the front, we have the CAN crystal. And then on the back, the blue pads there, that's a surface mount crystal. Those are kind of expensive, so that's why I had both options here. Those are the puffs for the crystal. Behind them, you can see the 2 resistors for the LED and the piezo. Piezo attaches right there. We have this nice silk screen outline of the 22 millimeter piezo. Got an LED up here in the corner. I mostly added that so I could hook it up to the scope and do frame timing. The buttons just hook up directly, so it's basically ground and then a direct I/O connection because I've enabled internal pull-ups. Pretty simple. There's not that many parts to it. Let's take a look at the back. Okay, so here's all these weird pads. So I have these as exposed pads, and all of these attach to, there's 2 pins. No, there's only 1 pin left over. So what I'm going to do is I'm going to enable the ADC on it and then connect all these pads to it, as well as this funky antenna. So I can use it to seed a random number generator using the analog digital converter. So I'm going to try JLC PCB for a change. I've heard good things about them, like the people on the EEV blog forums rave about it, but then I've also seen reviews that the quality isn't so great. When I went to order my parts, I couldn't believe how cheap it was. I mean, I've ordered circuit boards from China before, but even this kind of surprised me. I mean, it's like 35 by 78 millimeters. Total with a 2-day extra speed on the production shipping. The total was like $39 for 50 boards. You're talking like what, 79 cents a board. So I kind of wondered if I typed in something wrong, but well, let's see if it comes in the mail. Hey, look what just arrived from JLC PCB, and I ordered them 1 week ago. I clicked order 1 week ago, and here they are from China. So I guess this particular factory, its power was still on. Looks like everything is correct. There's the slots here. So this is the gameBadge. So you can clip this like a badge. Put the lanyard right here. Yeah. So what I'm going to do in this video is I'm going to show you how to stuff it, and then we'll see if it works. It looks, well, just cursory glance, at least at this one. Everything looks pretty good. It's cheap as chips. Bobby Dazzler. Bob's your uncle. Yeah, so I kind of took a shot in the dark with these because I didn't have time to test everything. So let's talk about surface mount soldering. So let's just go through each part. And I guess this could be used as a precursor if you're part of the workshop. It's also a much simpler project, assuming that it works. Okay, this is the LiPo charger. I haven't used this model before, but it was cheap. So when I put this project together, it's like, what's cheap? And more importantly these days, what's available? So as you can see, I tinned 1 pad, and then I slid the part into it. I guess I kind of just did that without explaining it. Now if we go to the other side, because I'm right-handed, a lot of people think, oh, surface mount soldering, you have to be super accurate, and no, it's more like you have to understand how the solder flows. So with this side, this is a SOT 23.5 chip. You can kind of just flood it with solder, and then you can just wick off the extra. Sometimes you can do this just with the iron, but I'm going to use a little bit of solder braid here just to wick it up. So then you wick it up, and then you just make sure everything is still, you don't want to wick up too much solder,
So you can put a little bit of solder on your iron and then just kind of go in and lift up, up, and away. Now when you're doing stuff like this, you always start with the lowest components first, or physically the closest to the board. Now this is going to be a 3.3 volt voltage regulator. Again, just a little bit of solder right there on the one pad. Grasp it with my tweezers. Now I'm looking straight down on it with my face. I'm going to heat up that one pin, slide it in place, and then let go. And then making sure I don't bump it, get the next pad. Now its position has been locked. Unbelievably cheap! Unbelievably cheap. Circuit boards is such a NIMBY thing with America. So really, it's not so much how much solder you flood in, it's how you remove it properly. So one thing I did for simplification was I put all the surface mount capacitors on one side and all the resistors on the other. So the front side, solder side, is the capacitor. So we've got 2 1 microfarad ceramics, mostly, oh wait, there's one there too, if I missed that one. These are for power filtering. So same thing, I'm right-handed, so I blob the solder on the right, heat it, bring the part in, and release. I was watching a Louis Rossmann video about Teslas hitting deer before actually I was watching it then. Both the trucks showed up. I was waiting for Bush Park and JLPCB at the same time, actually. For Osh Park, I got these. These are my Hall effect sensor recyclers. Hall effect sensors are kind of hard to get right now because Allegro is fabulous. It's fabulous and fabulous. So here's all the Hall effect sensors I've removed from Xbox controllers over the years to make single-handed controllers. And my idea is, since it's hard to find, well, it's hard to find any of those at all, to say nothing of through-hole, which is what I usually use. So I made the adapter so I can recycle the I can recycle the surface mount Hall effect sensors, and basically so I don't have to order more because it's hard to find them. Unprecedented times. Okay, now I have a couple of, well, I think it's labeled 22 puff, but I've got 33s, those should work. This is for the external crystal for the real-time clock. Well, technically it's a real-time counter, but as long as you keep power going to the unit, you can use the real-time clock to basically have a real-time, I'm sorry, I misspoke. This is based off the AT-Tiny 1 series, and they have a real-time counter peripheral. And if you attach that peripheral to an external crystal, like in this case it's a 72768 clock crystal, you can count in seconds, and as long as you maintain power, that gives you effectively a real-time clock. And then I have options here. You can put in a little can crystal, see the graphic, or surface mount crystal, even those are kind of expensive. I think I'll just grab a rando can crystal, one of the ratty ones, because I'll save the good ones for the actual workshop. Okay, can crystal goes through the through holes, bend it over flat, like that. And then in this case, I'm going to solder it from the front, so it doesn't flop around if I flip over the board. Just like that. And then once we know that it's in place, we can solder it from the bottom one at a time. That way it doesn't fall out. You might be wondering, what are all these pads on the bottom of the unit? Well, these are all hooked up to the ADC, so as you hold the unit, it should introduce noise, and we'll use that to drive a random number generator. All right, what do we got on the back? We got two 100s for resistors and a 2K, which is the charge controller charge programmer. Now, one negative is that I think it's only a 500 milliamp charger, so it's not going to charge super fast, but again, it was the cheapest charger I could find that was in stock. Okay, let's do these 100s first. Now this is a tape and reel. I'm just going to peel back the plastic to dump out the resistors that I need. Same thing, grab it like this with the tweezers and just heat it up. Heat up the tin pad and slide it on in. I could have got a different color, but it would have added like 2 days to the time. And also, you know, green is like, green just screams circuit board. You're going to wear a circuit board around your neck, everyone might as well know it's a circuit board. It's like I have copious amounts of all of these, so I think I probably don't even have to order anymore. So that's a 2K. I mean, you can put them on upside down, but you don't want the electrons to fall out. So I'm just going to make sure the black side is up with the label. Oh my gosh, I was watching a YouTube channel that I really like. It's called Game Hut. It's this, I think he's British. He's this guy who he used to work at Traveler's Tales. So he does videos talking about programming games, mostly on the Sega Genesis, which is cool because the Genesis doesn't get enough love online. Anyway, he was bodging a switch onto his Sega Genesis specifically to cause an error, and then he did an impression of me when he was doing it. He's like, "Oh, I'd better sing the Jurassic Park theme in order to make this work, like Ben does." And then he's like, da 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 da. So I thought that was pretty funny. And the video thumbnail said John Heck Hack, so I didn't realize his name was, is his name actually John Heck? And that was kind of weird to me because my little brother, well, he's my half brother, second marriage, but his last name isn't Heck, but his first name is John. So it's like, whoa, you know, it was kind of weird. Okay, same thing. So this is the ATtiny 1616. This is the newer line of tiny chips from Atmel/Microchip. They're quite a bit more powerful than the old ATtinys. They're still a 8-bit chip, almost like, well, obviously it's an 8-bit chip. It's also a 5-volt chip. We'll be running it at 3.3, which means we have to run it at a lower speed. I mean, we could run it at a higher speed, but you're not supposed to. So, versus the Argue Boy, which I also would argue, probably shouldn't be run at, if it's only, well, I would, yeah, I don't think it has a boost circuit on, so I assume that thing's being run at, they're running at full speed at 3.3 volts. I mean, you can do it, but you're not really supposed to do it. Again, same deal. I'm kind of doing a flood fill and then just cleaning up the excess. I like to flood the whole thing, and then I kind of hit it with the side of the iron and then creep the solder down the sides. 'Cause I'm a creep, I'm a widow. What the heck am I doing here? YouTube edit. Well, let's see if this fits. This is a Snap EDA part. Oh, it fit. I've been using Snap EDA for a lot of these Eagle parts. Well, Snap EDA will export all sorts of parts, but yeah, you go to Snap EDA, you type in the manufacturer number of a part, and it's got quite a bit of stuff on there. So I typed in the manufacturer number of this USB port, for instance, and then it's like, okay, how would you like to download the part? And I'm like, Eagle. Then it gives you the library, and it seems like it works. Same deal, I'm just flooding it and then removing the excess. Okay, here's the switch, same deal. Found the cheapest, most common switch off, I think it was DigiKey. And it fits. Nice. Let's get this switch out onto a tray. Nice. So I had the Z80 Note kit, and I ended up, that switch feels kind of mushy, but whatever. I ended up sending it to, well, everyone who was part of the workshop, I mailed them the kit. And kind of a pain to put those kits together. Anyway, for this kit, well, first of all, I didn't have much time. And I'm like, I'm going to make something that's really simple. So I think we're limiting it to 20 people again. Oh, so this is for scope probes. Yeah, I'm not that dumb. All right, tack switches. Felix brought home a bunch of surplus from MATC, Madison Area Technical College, including these tack switches. So I have quite a few of them. So I found a tack switch part, I believe it was Adafruit. I had to modify it slightly for these, but should still work. Now you might notice there's a hole in the center of the tack switches for the D-pad. That's so if I have time, I could 3D print like a D-pad switch, and then you could basically have that go over the switches and make it more comfortable to use. I mean, I guess, yeah, I just got to design it and then print, what, 20 of them? Yeah, so the workshop, I believe, I think it's $50. And it's going to be in the Bit Built section of MGC, which is, Bit Built is kind of like, that's like the evolution of the old benheck.com forums. They make a lot of really cool portable stuff. It's insane how far they've progressed it beyond what I was able to do. It's pretty cool. They like build Wii's inside of Altoids tins. It's pretty nuts. I will go back and just solder the other side. With these, you want to make sure that you see the solder wick down onto the pads, because sometimes you might get the solder to stick onto the pin of the tack switch, and you're like, oh, it's connected, but it isn't actually. That happens with pins on microcontrollers too. It might look like it's connected, but it's not. Oh, I think I used way too much solder there. The glob was too big, and it did not make the job better. I wonder if this will actually work. I hope it does. Although these PCBs were so cheap, they were cheap and fast, so I guess I could just order them again. Of course, my luck, I'd probably order them again. They're like, sorry, our plant is not getting electricity this week. And then I'd be like, no, like Darth Vader. Where is Padme? Is she safe? You killed her, Darth Vader. Why are there two headers for the screen? Can you guess? I'm sure someone can guess. Alright, so in this case, I flipped it over. Now, you want to make sure that they're straight. Of course, you can always adjust them later. So I'm just going to press down so they're flat against the table surface. Just solder one leg, then I'll visually inspect that they're straight-ish. Yeah, I did see some reviews that said, you know, you might get like bad pads or improper flooded vias, or vias that are flooded that you don't want to be flooded, or filled, I should say. But this appears pretty good. I'll clean up the flux after I'm done. Okay, so have you figured out the motivation yet? So it's like you have your screen and the signals are just duped. So you've got landscape. Then if you want to have a shooter game, portrait mode. Ah. And like half the comments is like, yeah, we figured it out, Ben. We're not that dumb. This LED is controlled by software. But if you put this thing into like sleep mode, because I think in sleep mode, this thing, even with the real-time counter running, it should last quite a long time. So, oh boy, here we go. So I found these on Amazon. It was like a 5-pack of 380 milliamp hour lipos. I think it's intended for like quadcopters or something. Yeah, I didn't have time to find the right connector, so I'm gonna have to solder it by hand. Oh boy, Wild Wild West. We get a wild Wild West. We're going straight to the Wild Wild West. All right, there's 3 wires on this. The middle one is for sense, I suppose. I guess if you want to sense vibration or something. So let's do this. Okay, so I got my hot glue gun, which isn't on. I'll be right back. Let's be really conservative with this. I'm gonna cut the black first. Strip it. Yeah, it should fit through there. Yes. Okay. All right, flip it over carefully. Well, you don't really have to be careful until you get the 2 poles in proximity to each other. Those lipos have a lot of power. You may have recalled hearing about a Galaxy Note in the news. Okay. Oh no, it's a giant metal spider. And that movie had like such good production design and special effects, and then all in service of a terrible, terrible script. Some special effects artists, and you're working on hour 500 of the giant metal spider, and you're like, oh man, I wish the script wasn't so awful. There we go. No voltage. That's not good. The outlaw trying to draw on the west. Not getting anything from the regulator. Mount up. Oh, did that pad not... Oh, I think I didn't practice what I preached. Like that pad right there. Where's my tweezers? Oh yeah, I don't think the solder flowed to that pad. The spice must flow. And the solder. Yeah, I don't think that pad is, or the pin is not connected to the pad. Well, the battery's off, or the switch is off, I should say, so I can flood it. So this regulator has, it has an input pin and an enable pin. Enable is active high, so basically you just attach the input voltage to both enable and input. I don't think it's attached yet. All right, I'm gonna hit it with some flux cleaner. I don't know if you can see that, like, see how you can still kind of see like the dull Hazel hot air solder leveling pad under that pin? Yeah, I think it's still not attached. So I'm going to add a little flux and then I'll hit it again. I think that's why the regulator's not working. The bigger the glob, the better the job. Yeah. Yeah, it was funny. He was talking about a Tesla, autopilot Tesla killing a deer. Like, I was driving down the road here in Madison the other day, and they got the electronic signs on the highways that say, like, 10,000 deaths last year in Wisconsin on highways. Let's get it down to 0. Or, well, it's probably not that many. It's probably like 2,000 deaths. But, yeah, I don't know. Just hitting deer is just kind of something that happens. They're actually one of the dumbest animals when it comes to the road. And I know it's like, oh, but they were here before us. And yes, it is true. Us evil humans, went to their domain and put roads everywhere. But most other animals are more intelligent. Like squirrels, ravens are super intelligent. Like if they're eating a carcass, they know, oh, if I hop half a foot to the left, I won't get hit by the car. Okay, that's got to be connected now. The thing is, if you see a deer, or if your Robo Tesla sees a deer, if you see one, that means there's probably 2. They're usually in pairs. Come on, baby. There we go. 3.29. You see one deer, there's going to be 2. There's different areas which you're more likely to see deer. Like if there's like if there's woods on one side of the road and a field on the other, that's like Deertopia. So part of the reason for the hot glue is to keep it just above the surface because there are a few vias there. Oh, and the red and black wires actually line up to where they're supposed to go. I totally planned that. All right, I hooked it up. The debugger is seeing the correct voltage, so I guess let's try programming it. Fingers crossed. Hey, it worked. Oh yeah, this is my demo. So I've got like kind of a gradient ship and then like a Shadow of the Beast background. Let's see, left, right, that works. Up, down, BA don't do anything. Got Mega Man and a sine wave there. Why is the speaker shouldn't be making noise though? That's weird. Did I change what port that was connected to? I mean, I can fix that in code. I'm gonna double check why the piezo is doing that. It's not supposed to. Because I built it using this. This was my breadboard version of this. And I think I had the piezo hooked up to PB4. Yeah, I think I might have got that backwards in code. Or, well, by that I mean I got it backwards when I designed this board. Oh yeah, that's what's going on. The noise from the piezo. Yeah, the piezo is hooked up to the LED frame timer, and the LED is hooked up to the piezo buzzer, so I need to switch that in code. Hopefully I can. Should be able to. But yeah, look at that. So you can get these amazing scrolling graphics. Just a few parts. Yeah, I just had them switched. Well, I did the PCB backwards, but thankfully they're both on different multiplexers, so now the LED is working properly. The LED actually is a waveform. You just can't see it. It's too fast for our eyes. And the piezo is making noise. Cool. Looks like everything works. The menu button is a bit gate kept by the LED, but I designed it that way. Yeah, so you don't accidentally reset your game in the middle of a heated battle. All right, well, we should probably talk about the code next.
Here are the OLED screens that I bought for this. It's a SPI-based 128 by 64 OLED display. Again, very much, well, pretty much exactly what's in the Arduino, just smaller. The thing that's nice about SPI is you can drive them much faster than an I2C screen, kind of like I used on the Z80 Note. I think I just ran out of I/O. That's why I had to use... Oh no, it wasn't because I ran out of I/O. I was having bus conflicts with the SPI screen and the SPI SD card. Well, anyway, let's talk about this screen. If you look at it online, it's usually called the SSD 1306 OLED display. So I drew this amazing diagram to explain it. All right, so it's 128 by 64 pixels, or 16 by 8 by 8 characters. So when you're filling the memory, it always, well, it can go in two ways actually. You can go in vertical strips or horizontal strips. I'm going in horizontal strips. So if you look at the upper left corner of it, it's actually made up of, like, see, I didn't even make motion graphics. I'm just dragging things around in Illustrator. That's how lazy I am. So each one of these would be 8 bytes, just like that. So when we send the SPI data, you basically send 8 bytes, that fills up this, 8 more bytes, fills up that one, goes to the end, repeats, and once you've sent 1024 bytes, the screen is updated. You can actually do it pretty quickly. And now of these bytes, see how they're oriented vertically? So obviously to make graphics, look, I made some pixels, right? So the upper portion, that is the LSB. So that would be bit 0. And the lower portion, that's the MSB, or bit 7. So like in this case, this orientation that I made, so let's say you've got all black, and then the lowest pixel is white, so that would be 80 in hex, because you've got 7 bits of black and 1 bit of white. Now the thing that can be tricky with this is if you need to draw something across a byte boundary. So it's written row, 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 your boat, like that scene in Star Trek V. Not the worst Star Trek, that's Into Darkness. So like if you're trying to draw a sprite, like let's say this is a sprite, So the horizontal doesn't really matter because as you can see, we've got horizontal bite stripes. What matters is if the sprite goes over a barrier like this. Now this is like if you're on a barrier like this, that's easy because the well, it'd be a 16 by 16 pixel sprite. It fits, even though it's offset in this direction, that doesn't matter because each one of these cells is divided into 8 horizontally anyway. But when this happens, what you have to do is you actually have to, instead of writing, well, you'd have to write 3 rows of data instead of just 2. And then you end up having to do bit shift operations, which are kind of expensive on an 8-bit controller like this. So like that, you actually would take, well, let's say you're halfway between. So you'd have to take the lower nibble and put it into that square, and then the upper nibble and put it into this square. Well, I mean, the code isn't difficult, but it definitely takes up a lot of time. But as far as drawing tiles, we can do that simply, that's pretty simple. Now, the thing that's nice about tiles is that it will save us memory. Let's talk about how the screen is oriented. There's 2 modes that I've created. So one is horizontal mode. Okay, so it's 128 by 64, which would be 128 of these character cells. So what I did was I set up 256 bytes of buffer. I call it the tile memory. And it's contiguous in this manner. So you write that, then you write that, then you write that, and so forth. So I've created a scroll window. So the scroll window, there's a command, it's set window and then XY. So how that works is like this would be 0x position. And then as you increase it this way, you see the window changes from the left-hand side to the right-hand side. Once you've gone this far, this would be at X position of 128. You're now viewing entirely the second window. Now, if you go past 128, like this, like 196, what happens is the first window repeats, and so kind of like this happens, right? Now, this is exactly how the Nintendo and most other video game consoles draw their tiles. And then once you actually would reach 256, then, I mean, this would already be displayed, but you would just reset the counter to 0 again. And the reason you do this, especially in something like the Nintendo was very slow at accessing its video memory because the CPU had to do it through the picture processing unit. So the Nintendo actually has a larger horizontal and vertical buffer than most systems. As your character is walking, you've got all of this space and this space to update the graphics before the viewport gets there. And conversely, if your character goes back, some of the graphics are already there. Now, this is different versus something like the Sega Genesis or the Mega Drive. Sega Genesis or the Mega Drive, I meant to say Master System, where that's like, you've only got about one column of graphics off the side of the screen. Okay, that was a horizontal. Now vertical, pretty much the same thing, except for it's like this. So it's the same memory space, it's just stacked this way. Now, as far as how it's arranged in memory, like when you want to access it, well, it's contiguous. So got 16, next 16, next 16. So really, it's actually a little easier than this method where you have to actually, like if you want to go from here, this pixel down to that pixel, you're actually adding 32 instead of 16 to the index. Yeah, so same thing. You have your window here. So you'd set X 0, and then Y would be Y2. You keep going down. That would be 64. The same thing. If you keep going past 64, it just repeats the top portion again until you get to 128, in which case you can keep going. The number will just roll over, but in reality, you should just reset back to 0. And that's pretty much how it works. You can use negative numbers as well. It'll just go this way. Before we move on to the sprites, we'll talk about how the tiles will be created. Now we're in Photoshop. Here is a very simple sample font. This is what I use in my garbage miner game. So I just drew this up as 128, and then this would be, 32 tall? I like to start at 32 because then you could just minus or subtract 32 from any value, and then it lines up properly, and then 32 being a space. So how this works is, well, same thing. And again, you could actually have wider characters if you wanted. There's nothing stopping you from doing that. You have 8x8 pixels, just like that. So there's your space. And these are what will be drawn to the screen. Now, how I do it with my tiles, since remember, this is all done horizontally. So if you want to go from, let's say this is 32 ASCII. So first of all, you minus 32, that gets you 0. And then you take the size of the character, which would be 8 bytes. And so you would multiply by 8, or you can do bit shift 3 to the left. And that would index it. So if you had a 0, obviously 0 times 8 is 0. You stay here. And if you had a 2, you'd end up over here for the quotation marks. So anyway, so you're like, okay, great. I have these graphics. Now what do I do with them? So the Arduboy people have a lot of, they have a lot of resources you can use online. I use this one called 2chars. I mean, there's others. So it basically just does the slicing for you. Okay, so I'm going to drag condensed font over there. And we're going to say we just want the whole thing. So 128 by 32. Then we hit convert. And then we see, there's our characters. I'm going to do that. We're going to grab that. And then our code, I'm using Atmel Studio, but your mileage may vary. Although I think you did do it the same way in Arduino. So we're going to do a constant char progmem, which means put this in Flash, and then we put in the data. So what we can do is we can have a pointer to the font, and then using the indexing we were talking about, we can figure out which tile to use. So in our tile map, which we had on the screen layout, so let's say this position of memory has, let's say that tile has a 16 in it. So we're like, okay, well, what do we draw? So we look at the font, we go 16, blah, blah, blah. Oh, that would be the number 0. So then what we do is we take 16 times 8, and then we use that as our pointer, and then we take that pointer and we point it to that index in this big long chain of numbers based off of the pointer of where this file starts. And that gives us our data. And then we just go through step 1, 2, 3, 4, 5, 6, 7, 8, and that draws the tile. It couldn't be easier. Sometimes I feel like I'm trying to see how boring I can make a screen capture video and people will still watch it. Okay, this is my MGC test app in Microchip Studio. All right, we got IO, interrupt, sleep. This is important. Remember, we have to run the CPU slower because of 3.3 volts. So I have a define here because if I don't, the delay function won't work. Okay, so the driver's gameBadge is actually my driver file. We'll get to that in just a second. And game would just include anything you need for your game, which, well, we'll get to that in a second. All right, frame flag. Okay. All right, let's see what we do for setup. Okay, change protection register D8. That means we're going to change a protected register. The register we're going to change is we're going to enable the prescaler for the CPU. The default, the LSB being 1 means it's going to prescale. The rest of that byte is all zeros. That means the prescale is divided by 2, which gives us 10 megahertz. So we got right there. We're going to set the inputs and outputs of all our pins. We do this for the SPI bus for the screen. Port B has some buttons. So a 1 means an output and a 0 means an input. Then this is the pull-up pin control. This is done a little differently on this particular chip. So I have to set these for all the buttons. It's got this, I mean, it's kind of handy because you can do it like an atomic operation. See how it's got like, oh, this is bit 1, 2, 3, 5, 6, 7. So we're inverting the logic, which is also good because it saves us time. So normally the pull up internally would have it pulled up to 1 volt, have it pull up to high. Then when you push the button, it would bring it down to 0. And then, but when it comes to logic, you'd be like, oh, if this and that. But if it's 0, that means you have to invert the logic. So by inverting the output of this, we can say, well, I'll get to it in a second. Okay, so this is important. This starts the SPI bus. And we have it set to double speed, so the SPI bus, well, normally the SPI bus runs at half of the CPU speed, but it's doubled, so it's back up to 10 megahertz. Woo-hee! Setup display. Okay, this is in gameBadge. Let's go to gameBadge. Obviously, I've done a lot of this. So this is just the standard commands to set up the SSD 1306. You can grab these off GitHub. Tons of people have written this, so just go online and steal it. It's just sending a bunch of commands, and then I have a write command function here. It does the data or command pin. Low means it's a command, high means it's data. Chip select's activated, then it sends the SPI data, then chip select goes high again. This sets up the display. So once we've done that, now we switch the SPI bus to high speed, well, not really high speed, but we switch it to double buffered mode. So this means we can write 2 bytes at a time at high speed without having to wait for the first byte to be completely sent. That'll save us some time. We do that after we set up the display though, because when you're sending single byte commands, it's easier just to send 1 byte at a time. Okay, so we got a couple things here. We're using 2 of the timers so far. We have the frame rate timer. We're using timer B0. We're setting it up. Its period is, okay. Well, this information that I wrote here is completely irrelevant, at least most of it is. Okay, clock divided by 2 equals 5 megahertz. That's how fast the timer is running. It's running at 5 megahertz. Okay, so if we have 5 megahertz, and then see how we're counting to 5,000? See that 5,000 there? So divide by, oops, divide by 5,000, 1,000, and that gives us a 1 millisecond timer. Huh? Makes sense? So that's why you have to RTFM. So you're like, oh, I divide the clock, because the sources for these timers is usually a division of the clock. So we can't actually technically get 60 frames a second because that's 16.666666 milliseconds. So I'm actually going to run this at 50 because it's easier to divide. So what this does is it sets up a 1 millisecond interrupt. All right. Now let's go look at why that's important. We have an interrupt service request down here. So every time that 1 millisecond, every time a millisecond passes, the frame flag will increment. We'll do some logic for the piezo speaker, and then we'll clear the flag. So in the main loop, all that it does is say, hey, has 20 milliseconds passed, which means 50 hertz? If so, clear the counter and run game frame, which is your game logic. So then that's your interrupt-based 50 hertz locked game logic routine. Then we have TCAA. So this is a piezo sound, the new Dolby Atmos. So we're just going to create a waveform on the speaker, and then mux control sets it to the pin. But this basically just makes the buzzer tones. And so that's pretty much it for system setup. We set up 2 timers, one for the frame rate and one for the audio. I will set up a real-time clock and a sleep control later on. And for instance, the sleep control will probably disable, well, it will disable the millisecond counter, but we'll get to that later. All right, so let's look at game, right? So in the main function, which is called first, we call game setup once. Oh, that enables interrupts. Wait, it's labeled. You could probably figure that out by reading. All right, so game setup gets called once. And all I'm doing here is I'm setting the scroll direction as I talked about. So this is the function in gameBadge C that I made. gameBadge C being the drivers. Memset, I'm taking the tile map, which is, this is the 256 byte tile map we talked about. I'm clearing the memory to 47, which is just a blank character in the character set that I made. Then I'm making the clouds. So this creates the clouds and whatnot from the image that you saw, the Shadow of the Beast Gradius thing. So that just draws everything. It's not, this isn't really efficient at all. It's just a test. Okay, so then 50 times a second, game frame is called. So right now I have it turning on and off the LED at the beginning and the end. That's so I can see using a scope how long this takes. I could also create a function where I look at the value of the counter function and see how much of 5,000 counts has occurred. Let's take a look at each piece of this. Gamepad equals screen load. So I kind of combined those together. Let's see, we're screen. Okay, here we go. Okay, so chip select low and DC is high, which means anything we send to the screen is going to be data, as in data to fill the screen. So 512 times 2, you still have to wait for the data to be transferred from the input buffer to the output buffer, which is what this does here. But you can basically load it faster than you would with a normal non-double buffered SPI. So that's why we send 2 bytes at a time, which makes it faster. And then here, the buttons, oh, I guess that's what port C is for. The buttons are on port C, and a couple of them are on port A. So we can see we have, this is the up, down, left, right, F, which is 4 bits. And then the upper 3 bits of port A, which is E and hex, and then return that value. Okay, the next thing we do, we draw the tiles because, so picture it like this. It's like everything that you want to draw, the things in the background you draw first, and the things in the foreground you draw last. So the background is the tiles. So we got the draw tiles function here. This is where the magic happens. So I have it split into two. So there's a vertical version, which is this, and a horizontal version, which is somewhat simpler. I don't want to even get into all this. It would just take too long. But you can see here, remember when I talked about the bytes having to be combined across borders? Like that. That's what's happening here. So it's got like an upper and lower nibble. And then it looks to see if it's on an edge, blah, blah, blah. But then here, this is horizontal. See how it's much, much simpler? We don't have to do any bit shifting. We just dump all the data in. And then we just have a bunch of math. There's some stuff I did here where I use unsigned and signed values, and I use the fact that the screen is, the screen is a power of 2, 128 by 64. So you can actually use that to your advantage. This video is going to be too boring. I'm not even going to go into it too much. Anyway, that draws the tiles. And then you can also, as I talked about, you can also have a scroll value to the tiles, which we'll get to in a second. Actually, I'll just scroll down to it now. Haha, scroll. So you can scroll the whole window, which I think I have a command for. Yeah, set window. That sets the whole thing. Although each row has a separate scroll value. So for the Shadow of the Beast kind of thing, I have 8 separate scroll commands to make the screen move at different rates. Although the middle 3, which is the mountains, they move at the same rate. So you can do either or. So if, like, let's say you wanted to have, a status bar at the bottom that doesn't move, then you would just scroll the top 7, and then you would not scroll the bottom one. Pretty easy. Okay, draw a sprite. I definitely don't want to get into this one. All that you need to know is that it works. Beast tree is the graphics, and this is done kind of the same way as the tiles, although it's a little more complicated, so I'll get that in a second. So beast tree, so that's a pointer to some prog mem. So this is the XY size of the sprite. Now the X size doesn't have to be on a boundary of 8. I just usually do it that way because, I don't know, because I do. But the vertical size has to be on a boundary of 8. And see how I have 2 lines here? So that's the mask and the pixels. We'll explain that in just a second. Go back down. Okay, so it's data, X position, Y position, frame number, and then if it's mirrored. So if it's 1, it's facing right, or 1 is basically facing the way you drew it, and then -1 flips it horizontally. That way you can save memory. So then you also have the ship, and then all this stuff here. This is just me making the stuff move around the screen. And then, we talked about the logic there. So if gamepad and D up. So gamepad is the variable that gets returned from screen load. So this is why it's handy to invert the logic. So you just do if gamepad and game up, then code. So otherwise you'd have to do if not gamepad, and that's one more thing for the processor to do. So basically all this does is just move everything around. Tone, this is what tone in frequency-ish, and then how many milliseconds to play it for, so you can have automatic tone. And fill tiles, I was using this basically to fill contiguous tiles. All right, so let's talk about how the sprites are done. Here is the beast tree as seen in the example, and I did copy this from Beauty and the Beast, Altered Beast, Shadow of the Beast. All right, so I've got multiple layers. There's my layers. I had to reinstall Windows, so some of my settings are kind of funky. So if you look at it like this, that's what I want it to look like on the screen. So the pink pixels are the transparency. However, if you remember, these are all monochrome graphics. So how do we do transparency with monochrome graphics? I thought you'd never ask. So the first thing you do is you draw your tree like this, and then it's got like a black trunk, and then the leaves or whatever. So then what you have to do is you have to create a mask. And let me just show you what that looks like. I'm going to turn off that layer and turn on the mask. Now see how it's slightly bigger? Let me turn off the color overlay. Okay, that makes it black. Okay, so that's the mask, and then in a foreground layer, I have the pixels. So see how I offset the mask a little bit to the left to give the tree kind of an outline? And you could also just outline it as well. So how this works in the code. Okay, so bear with me. So first of all, the mask has to be white. So you have it like this, and what happens is, so pick these, the white is 1 and the black is 0. So in the code, it takes us in bit by bit, and first it has to subtract this from the background. So you might have existing tiles. So you have to basically cut a hole in those tiles in order to draw the new pixels. Well, I don't think I really need to explain what this would look like inversed. So what happens in the code is when you bring this is how the data actually looks. But when it goes to draw it, it actually will invert the values. To make your mask, so you might draw the tree like this. Oh, it's got nice transparent pixels, but then you need to make a mask. You need to make the mask white, and then for both things, the pixels and the mask, you have to export it with a black background. So you've got this here. So of course, Photoshop has changed everything again. Okay, so let's turn off the tree. Let's turn on the pixels. We still want the black background, so this is going to be the beast tree pixels. So we're going to go export. Cool. Now we have both masks. All right, where's that 2chars program? There it is. Let's start over. All right, so we're going to start with the mask. So I'm going to grab the mask PNG. Okay, so 40 by 40 pixels for the tree. All right, so there's our mask. So we're going to grab that. We're going to put it first. So each frame, well, the way I did the sprites, it's kind of like the RG Boy. We have this position of memory. We have the XY position. Then after that, we have frames. Each frame consists of the mask and then the pixels. So it'll draw the mask first because it has to subtract that from the tile background. Then it'll apply the pixels over the black hole, your favorite movie, that it cut into the background. That was a very interesting failure of a movie. I miss the days when Disney would make interesting failures of movies. Now they just make failures of movies. All right, so here's the tree pixels. All right, I'm going to put that right after it. All right, so we have the size of the tree, 40 by 40. Now, as we mentioned, it's horizontal bytes, and then it's 1 byte for every 8 rows. So the second one, you can't just go 40 by 40. That's not the, well, that's how many pixels it is, but that's not the memory size. So the second 40 divided by 8, 5 times 40, and it's actually 200 bytes in memory. Now that's 200 bytes for each one, so that's 200 bytes for the mask, 200 bytes for the pixels. So what the software does is it doubles that for 400. So if you have a second frame of the tree, then it jumps 400 positions in memory to draw that if you specify the second frame. So if we had a second frame of the tree where like the leaves were blowing like ghouls and ghosts, we would put that there and then the next frame there until we run out of memory. And so which means when you're cutting this up, if I've got like a sprite sheet like this, I actually have to cut it up bit by bit, row by row to make this video game grow. So I have to crop down to this, send that as data. Then I got to crop down to this, send that as data. And that kind of slows you down, but it makes the math easier on the sprite side. Let's talk about how this was all put together. Okay, so this is my drawing. This is what I use to kind of map out what the screen should look like. So I've got the tree, I've got some mountains, and I've got like 2 layers of foreground grass, and I've got some clouds. Now, obviously, if you had all these pixels in memory, that would cost you 1,024 bytes, but that's why we use tiles. Then if you look, I actually did some tricks here, like this mountain, for instance. See how I actually made it so it doesn't use that tile or that tile? And I did that on purpose. Seriously, no, I really did. That way it saves some memory. I mean, if I probably could have skipped that tile too if I just drew the tip of the mountain a little bit differently. So what I did was I took those and I turned them into this tile sheet. So this actually is all the tiles that are required for the screen. So this would be 0, 1, 2, 3, 4, blah, 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 16, blah, 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 what, 32? Yeah. Then remember how I had 47 to clear the memory? So that's one of these out here. So it's just blackness. So yeah, so I just took this into 2chars and I created a file and then I brought it in and it is right here. So tile data. So tile map is the RAM. So tile map is the RAM where you put each thing, right? So that would be position 0. Tile data is the data used to actually draw the tiles themselves, or the pattern tables, as they would have called them in the days of lore or yore, or the days of before, the olden days. All right, so let's look like a minimal viable example. All right, so game frame. We're going to load the screen. And as we mentioned, that basically just dumps the frame buffer onto the SPI device as fast as we can. And then we draw the tiles. So we've got 2 pointers here. We got the tile data, which is the data to draw the tiles, which is this stuff. And then we have the tile map, which is the RAM, which is this stuff. Now, if you might recall, well, you probably don't recall because I skimmed past it. Like when we drop the clouds, drop the clouds? When we drew the clouds, like right here, fill tile, position 0, 3. So what that's doing, if you look down at fill tiles here, so that's location in the memory, starting tile in the tile map, and then how many. So we're saying, okay, on the second line, I want you to draw tile 0, which is this, and then draw 2 more to the right for a total of 3. So that draws boop, 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 draws a cloud just like that. So this should create a static display. And there you go. It's a static, serene countryside where nothing is happening. An idyllic age before the shadow of the beast arrived. And then you had to go punch a toe 500 times to beat the game. I mean, you could draw the sprites first and then draw the tiles, although the tiles would overwrite everything. Of course, you might not even want to draw tiles, in which case you go into gameBadge and just get rid of that buffer and reclaim 1 kilobytes. 1 kilobytes. Okay, so Beast Tree. So this is going to be the Beast Tree graphics, which is a sprite, which is right there. See, so we got the mask and then we got the pixels, so it's just 1 frame. Then we have the X position. It's always in the same spot of the screen. And then we have it on a byte barrier, so it will always draw very quickly. Like if we change this to a 7, it would start having to draw the tree across byte barriers and slow everything down. Like it slows it down a lot. 0 is the frame number, and then tree flip. So every time the tree goes off the screen, we'll change this from -1 to 1, and that will just make the trees look like they're mirrored. Let's try that out. Hey, there we go. The tree is on the screen. Cool. Okay, draw sprite, ship 20. Let's put the ship a little closer to the middle of the screen. Y position ship frame. Let's add ship dir, so we're going to turn left and right. Okay, so after we draw everything, so if gamepad ND up and Y is greater than 0, then go up, ship frame 2. If down and Y is less than 48, go up, ship frame 1. Cool. Now let's see. Let's make the ship go left and right. Now here we can see we had all sorts of code for doing the fake parallax scrolling. I'm going to get rid of most of that. I mean, I'm going to restore it because, you know, the parallax scrolling is cool, but we just need, what are we using? X, I think? Yes. So let's see. Ship dir equals -1. Let's get rid of the tone. And yeah, how lazy can Ben be? The answer is this lazy. He stretched out his arms and was lazy. Now that alone won't do it. Remember, we have to do set window. Now we were doing individual scrolling, but set window will scroll the whole screen. There we go, set window. I mean, why did I look that up? I clearly knew what it was, or did I? Okay, so X and then 0 because we're not vertically scrolling. Let's try that. Ship going left and right, but you'll notice the tree and the debris aren't moving because we don't have them updating with the background. And also notice how the ship does not reset to the straightforward position. Let's make the tree move with the background, and then we'll make the logs move faster in the foreground. Okay, so if our player moves to the left, that means the tree moves to the right. And the tree is attached to the background, so it's moving 1 pixel at a time, just like the background is. So that should work. So if it goes off the right-hand side of the screen, we put it off the left-hand side of the screen, which is why I made the sprites work with negative numbers on both the X and the Y. Basically, so you can delete them. Or if you don't want them to show up, you can draw them off the side of the screen, or you can just, not draw them. So we'll just do that. That should work. And let's see if the tree behaves. Oh, good. The tree is quite literally firmly rooted to the ground. Oh no, what about this pesky debris that's in the foreground? We want that to move faster. Okay, well, we'll do it the same way. We'll just move it 2 or 3 pixels at a time. Okay, so let's move the debris. So we're going to move that by 4. And same thing, I think it's the same width as the tree actually. So +4 -4, and then if it's less than -40, we'll repeat it to the right-hand side of the screen.
It should work. Yep. Now you probably want to, bake these fake parallax movements into a separate command instead of having them right with the player motion logic, but this is an example. Okay, so what about the fact that, so we see the underbelly and the overbelly of the plane there, but we don't see the straight ahead view, so we need to have something that resets it back to the frame 0.
It's actually really simple. So after we draw the ship frame and before we take the controls, we'll just say ship frame equals 0. Default. So if the player doesn't continue to hold the controls, the ship will return to its default graphic once the player lets go of the controls.
Now, this should work. Okay, up and default. There we go. Down and default.
Okay, let's reintroduce some of that fake parallax scrolling. So we set window X0, so that sets everything, but we could also individually set values if we wanted. So we have our X scroll register, so bit shift 1 to the right, so that divides it by 0. So that means the mountains will only move every other pixel versus the rest of the display. Conversely, if you want the foreground grass to move faster, we go set row scroll X times 2 on rows 6 and 7. Let's give that a try.
All right, there we go. The mountains are moving at a different rate than the foreground, and see how the trees kind of attached to the clouds. So that's, if you wanted to make so if you had like a multiple scrolling thing and you wanted to like fake it, you could like draw a column with the sprite, which is exactly what most TurboGrafx 16 games did, because that did not have a spare background layer.
So my idea is I'm going to put this sample file on GitHub so you can download it and create your own programs or convert this to Arduino, I guess. Yeah, so if you look in the Solution Explorer over here, so you've got main, which is always what gets run first, no matter what. This sets up all the I/O in main void, and then it just does the while loop, which looks for the interrupt, which triggers the game frame. So if you wanted to change the speed or the frame rate, you could do that here as well. Just make sure you don't run out of time. Then game C holds your game. Obviously, you can add other functions here. Don't forget to put them into the game H file, otherwise it won't work. The compiler will, complain. I mean, I guess you could put the function prototypes up here. Or if you want to be really sneaky, if you wanted to call something without prototyping it first, you could just put it ahead of the thing that you called in. But that's really sneaky. Yeah, you shouldn't do that. That's, it's going to kamikaze. Oh, so one thing I did here, like when we had the floating Mega Man, I went online and found like a HTML program that would generate a sine wave. This is what all the old games would do, like the Medusa heads in Castlevania. It would generate, you would just pre-generate the sine wave and then use that for everything. So if you want to make something move in a sine wave, you just assign it these values. And if you want it to move in half the height, you would just divide all these values by 2 or multiply them by 2. It's pretty easy to use. And then, yeah, going over this again. So these are the sprite graphics. So it's the XY size and then frame. So the ship has 3 frames. Mask pixels, mask pixels, mask pixels. Tile data is actually the pattern data that goes into the tiles. And tile map is the RAM that holds the tiles. Originally, I had the tile map RAM in this file, but I moved it into the main file just so you could access it a little faster without having to use functions for everything. Yeah, then I just have a bunch of variables here. It's a big, huge mess. Then game setup is run one time when the thing starts. You could actually switch scroll directions mid-game. There's nothing stopping you from doing it. Just remember, vertical is much slower. So you probably have like your main state machine here and then branch off into other code depending on what you want your game to do.
Hopefully this was a decent overview of how to assemble the gameBadge and how the code works. Again, you could write your code entirely from scratch if you want, but I just created some Arduino-like libraries to get you started. And as you can see, you can make some pretty cool graphics. This is using 3.9K of flash. Probably half of that is just the graphics. And then 1.3K bytes. So you've got 1,000 bytes of screen buffer and then 256 bytes of your tile map, which leaves you 750 bytes for your game variables, which isn't really that's not too terrible. I mean, look at this thing, it's tiny. Yeah, so I'm going to put all the files on GitHub so you can make your own. I'm not going to sell kits, but I would mail out spare circuit boards unpopulated. So yeah, if you're interested, I guess take a look. And if anyone is interested in like doing an Arduino fork with what is it called, tiny core libraries, that would be great because I don't want to bother doing it. Because this project is kind of a rush anyway. But yeah, I mean, it shows that you can get some pretty cool graphics just using an 8-bit microcontroller and lots of ands and ors. Dun 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 dun. Speed up. Dun 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 dun. Hover dun 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 double. Dun 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 dun. This thing scrolls a lot better than the MSX one.